Welcome to today's Explainer. If you've ever wondered how we essentially trick rocks into thinking, you are absolutely in the right place. Today, we're diving straight into Chapter 1, specifically sections 1.7 through 1.9, to build the universe of modern electronics, right from the ground up. We're taking a fascinating journey, starting with the tiniest mathematical constants of our universe, establishing our core definitions, and ending with the complex semiconductor devices that power our everyday lives. Here's our roadmap for today. First, foundational constants. Then, classifying solids. After that, we'll hit physics vocabulary, semiconductor properties, and finally, devices and photonics. Let's get right into it. Section 1. Foundational constants, the universal numbers. We're talking nearly 300 million meters per second, the speed of light in a vacuum. It's essentially the universe's ultimate speed limit, or, its absolute cheat code. In the realm of physics and electronics, you just can't negotiate with these constants. They're the fixed boundaries within which all of our electronic engineering must take place. Now, let's talk about the heavy hitters. These are the vital building blocks that govern quantum behavior. Take a second to consider the incredibly tiny mass and charge of a single electron, because these are the actual physical actors in our circuits. We've also got Planck's constant and Boltzmann's constant in the mix. These specific values dictate exactly how energy is transferred and how temperature affects our materials. When we talk about how an LED lights up or how a transistor switches on, these are the mathematical rules operating behind the scenes.
All right, Section 2, classifying solids. Taking these numbers and looking at the actual materials we engineer.
So, we have this massive night and day contrast in conductivity between different types of solids. On one hand, you have conductors, like copper, which just let electrons flow completely freely. Then, on the totally opposite end of the spectrum, we have insulators, like porcelain. They have a remarkably low conductivity, essentially blocking electrical flow entirely. But why exactly does that happen? Well, it all comes down to the atomic level. Specifically, energy band gaps. Think of an insulator as having a massive, literally impassable canyon between the valence band, where electrons normally hang out, and the conduction band, where they can actually move. But with a conductor, those bands basically overlap, meaning electrons just breeze right through into the conduction band. And sitting perfectly in the middle is our hero, the semiconductor. It has a gap, sure, but it's small enough that with just a little nudge of energy, electrons can easily make the jump. Now, to get those highly specific, useful energy bands, the atoms themselves have to be arranged absolutely perfectly. You can think of crystalline lattice structures kind of like 3D Lego scaffolding that gives materials their unique structural integrity. A diamond lattice, for instance, relies on a single elemental material, creating a repeating, interlocking cubic structure, which is exactly what silicon does. A zinc blende lattice uses that exact same intricate scaffolding, but it alternates two different materials, like gallium and arsenic. Moving right along to Section 3, Physics Vocabulary. Let's define our macroscopic actors. Okay, this is where human engineering really steps in. An intrinsic semiconductor is purely native material, like a pristine silicon crystal. It's unmodified and, frankly, on its own, not actually all that useful because it doesn't conduct very well. But an extrinsic semiconductor, that's where we've deliberately introduced impurities to take total control of its electrical properties. It is a real game changer. We create those extrinsic materials through a process called doping. We're essentially baking specific impurity atoms right into the crystal lattice. We use donors, which are atoms that literally give away an extra negative charge or electron to the crystal, or on the flip side, we use acceptors, atoms that take an electron, leaving behind a positive empty space in the structure. And this doping process is so cool because it reveals the dual nature of electrical current in semiconductors. You see, it isn't just about the movement of negative electrons. When an electron jumps out of its place in the crystal bond, it leaves behind a vacancy. We call this a hole. Even though it's literally just the absence of an electron, mathematically and practically, it acts exactly like a mobile positive charge zipping around our crystal. So, depending on which specific dopants we use, one of these carriers, either the electrons or the holes, is going to totally dominate the material. The one we have the absolute most of is, naturally, the majority carrier. The one that becomes scarce is the minority carrier. Simple enough, right? To keep it all straight in your head, just remember this super basic naming convention. N stands for negative. Therefore, an N-type material has negatively charged electrons as its majority carriers. P stands for positive. meaning a p-type material relies on those positively charged holes as its majority carriers. And by slapping these two types together, we create the absolute foundation of modern electronics.
Section 4, Semiconductor Properties. Let's see how these materials actually power the modern world.
When we look at the actual band gaps, the hard data proves exactly what we were discussing earlier. Take diamond. It's an insulator because it has a massive 5.5 electron volt barrier. It takes an immense amount of energy for an electron to jump that canyon. But look at silicon at 1.12 eV and germanium at 0.67 eV. They sit perfectly in that semiconductive sweet spot. It makes them incredibly easy for us to control at room temperature. But, beyond just band gaps, we also have to look at mobility, which is how fast those electrons and holes can actually move through the material. Silicon is our reliable everyday workhorse for sure, but check out that incredibly high electron mobility in gallium arsenide. That specific property is exactly what dictates which material engineers grab when they need to build ultra-fast, high-frequency devices. Finally, Section 5, Devices and Photonics. Let's look at the real-world applications. The transistor is, without a doubt, arguably the most important macro invention built from this micro vocabulary. Whether you're dealing with a field effect or a bipolar junction transistor, it's essentially a three-terminal device. You apply a tiny little signal to one terminal, and it controls a massive flow of electricity between the other two. It is the ultimate electronic valve, and literally billions of them are sitting on the chips inside the device you're watching this on right now. And beyond just switching current, we can actually bridge the gap between electricity and visible light through optoelectronics and photonics. By engineering those N-type and P-type junctions perfectly, we can force electrons and holes to recombine. When they crash together, they release energy. In materials like gallium arsenide, that energy is released as photons. That whole shebang gives us LEDs for our screens, laser diodes for fiber optics, and photodiodes that do the exact reverse, absorbing light and turning it right back into electrical current. So, with this foundational lexicon established, you now hold the keys, the vocabulary, the math, and the constants to decode the electronic magic happening all around you. Every screen, every smartphone, every laser, it's all just a highly engineered manipulation of electrons, holes, and band gaps. The next time you turn on a device, ask yourself, what microscopic dance of doped crystals is making this exact moment possible? Thanks for joining me on this explainer, and keep exploring.